Hello, let me explain how to perform the projectile water experiment. First, why do we perform a projectile water experiment? Water is crucial for firefighting. And when water is used in firefighting, the motion is a projectile motion. So as we are studying the projectile motion, here we want to study the projectile motion of water. So that first help us understand projectile motion, and secondly helps us understand using water to fight fire. It's for our safety. So this experiment, there's a demo video. If you open this, you're gonna see how the experiment actually runs. So what you're gonna do is you're gonna get a water bottle, punch a hole, and fill the water and tightly close the cap. One thing that's really interesting is, if there's a hole, you put water in it, water will flow, keep flowing out. However, as soon as you tightly close the cap, the flowing will stop. In other words, if you don't squeeze the bottle, the water will stay inside the bottle. For that, we will be able to explain when we get to chapter 9, studying the internal pressure of water and the Bernoulli's principle. At this moment, we do not need to worry about that part. We only need to study the projectile motion of the water. So you are expected to do next is to open the cap, see how the water flows, and figure out how to make measurements, and then close the cap to see how water is stopped. Each time you repeat the experiment, you need to fill more water into the bottle, and so that the experiment always start at the same water level. So the first part is to set it up and practice running the experiment so you know how to start and stop the water flow, and also figure out how to make measurements. For example, you pick whether you use a ruler or measuring tape to accommodate the range of the X direction displacement. After that, the next step will be to study the water's motion along the vertical direction. So that does not mean you have to make this measurement first. You can make the measurement of the hole's height relative to the bottom of the tray. You can measure this even before you fill the water, or you can measure this after you finish the other measurements. Either way, you need to measure the height. In this diagram, this picture will actually show you the total water height, as in big H, capital H, and the lower case h represent the distance from the top of the water level to where the hole is. Instead of just show you the height of the water, I put in here because I want you to pay attention. How far and how high the water can reach depends on the total height of the water. And that is also that I want you to share with people around you in order to maintain water pressure. And that would be crucial for fighting fire. It's important to make sure that we do not waste water in the summertime, especially do not play with fire hydrant, especially on hot summer days like the days we're having lately. Okay, so that's to use this measurement height. So you find out how high the hole is, which is capital H minus the little h. We use that in the free fall pattern. Free fall pattern of the motion is the vertical direction. So we learned to divide a problem into two parts. So for this problem, even it's a lab problem, we still apply the same problem solving strategy. So we're going to divide this real world problem into two parts. The first part is the vertical motion. The vertical motion is the free fall pattern. And for that, if we know the initial height of water, the initial velocity of the water along the vertical direction is 0. Why? Because it came out horizontally. So the initial vertical velocity of the water is 0. So then we know the vertical height. We also know a constant, which is the gravitational acceleration, 9.8 meters per second squared, pointing downward. So we know three things. Initial velocity along the y direction is 0, free fall acceleration, and the height. Using the three quantities, we can apply the free fall equation of motion and solve for the time it takes for the water to fall down to the bottom of the tray. Okay, so this is the second part. So the first part is to set up the experiment and run the experiment. Second part is to solve the free fall motion along the vertical direction. Okay, and the last part is to solve the horizontal motion. For this real world problem, as I said, we use the slicing problem solving strategy. That means we divide a complicated problem into smaller solvable parts. So the next solvable part is the water's motion along the horizontal direction. Once water leaves the hole, it keeps going forward at the same exact horizontal velocity. And this is true for this as well as all other projectile motions. So for that pattern, one-dimensional motion with a constant velocity, we can measure the horizontal displacement, which is the R in this case, in the picture. And we also figure out the time from the free fall motion. So we're going to use the time. So if we know the horizontal displacement, if we know the time, we can calculate the initial velocity, which is the constant velocity in the horizontal motion. And then we get the conclusion, what the initial horizontal velocity is. And that's the end of this experiment. Okay, later in chapter 9, we're going to apply what's called the Bernoulli's principle. That tells us how the pressure difference between the top and the hole can actually create this velocity. And that also helps us to understand that it's important to maintain water pressure. We have water on the third floor of our physics lab building because the water pressure is built by water tower. So it's always the water tower that creates the water pressure. And sometimes you use pumps to pump into towers. Anyway, so our experiment is to study projectile motion of water, which is made up of two parts. Horizontal direction is a one-dimensional motion with a constant velocity. We make measurements of the displacement. Vertical direction is a free fall motion pattern. We make measurements of the displacement. I also want to point out, we do not measure time in this experiment. We do not use a stopwatch or any other equipment to measure how long does it take the water drop to reach the bottom. As a matter of fact, it's very difficult to keep track of the water given the equipments we have. So that's the design of the experiment. And I hope this helps you understand better, first, the projectile motion, and secondly, how important it is to have water pressure for fighting fire and for our safety.